My name is Nathan Crock. It's a pleasure to meet all of you. My background is in computational neuroscience. I worked at the Max Planck Institute, Florida Institute for Neuroscience for many years, studying astrocytes in the visual cortex and trying to develop some modeling techniques to help us understand them. And that data is very high dimensional and very complex, which lends itself to the analysis of artificial intelligence. So I ended up using those tools, kind of falling in love with it, and then my research focus kind of ended up converging into some of these cutting-edge AI techniques. In particular, I left academia, and I'm working as an AI engineer. I'm trying to take these really cool technologies and make them improve the health system in particular, which I'm sure everybody knows needs a lot of work in the United States. But I also have the luxury and opportunity to continue working with a bunch of talented individuals like yourselves here at the university, in particular. Dr. Matt Cooper Borkenhagen at the back there is one of my collaborators in the work that we do here, and some of our students as well. So what we're going to talk about today is going to be probably the first half, or a little bit more than that, is just some AI fundamentals. I'm going to try and lay the foundation of how these large language models work to help stoke your intuition about that. And I'm going to keep trying to draw parallels back to reading research to make it relevant. And then towards the very end, I'm going to talk about our cognitive reading model that we created and some of our preliminary results. Okay. Hey, welcome, Dr. Wagner. Mostly, this is supposed to be like a hybrid between like a workshop tutorial. Like I would like it to be very pedagogical in nature. So just, interrupt. Let's make it interactive. You probably heard the old adage, tell me and I forget, show me and I remember, but let me do and I understand. So you'll get the most out of this by interacting. So ask questions at any time. All right. So let's go ahead and jump in. So this is going to be what we'll cover. First, I'm just going to kind of start off with a little demo to get some sparks and fireworks going to make things exciting. And then I'm going to do some just basic foundational stuff of large language models, kind of focusing on aspects of it that I think are most interesting to reading researchers and psychologists. So we'll do the overview of representations in particular. I know is an interesting topic, particularly in reading research and in neuroscience in general. And then we'll do a small little kind of behind the curtains peek into what's going on under the hood, but try not to get too technical. Then I want to spend a little time just kind of showing you how large language models have evolved over the past 6 years, right? The GPT came out, and that was supposed to be all fun and good, but then suddenly ChatGPT came out and blew the whole world away. What's so special about ChatGPT versus the original GPT, and where are we now? So I'm going to do a little step-by-step evolution about that to help build some intuition there. So in particular, we'll talk about pre-training and how expensive it is and how important it is. Then we're going to talk about transfer learning, which I think is a really important general concept that is interesting to machine learning researchers, neuroscientists, psychologists, et cetera. And then we'll talk about agents a little bit at the very end. So finally, I'm going to jump into the reading model using all the foundations that we just discussed. And the reading model, we'll just talk about the architecture, why we designed it the way that we did, relating back to some of the fundamentals that we started with. Show some very preliminary results. This is all just experimental. And then show off the team a little bit. And then we get to just chat and eat some more pizza. All right, so let's start off with GPT-4V. So let's do a demo here. All right. So I don't know how many of you guys use this stuff, but let me just show you. So please search the internet for the latest valuations of Microsoft from 2020 to 2024. Then present the results to me in a table with one column the year and the other the valuation. Next, create a plot of the valuation as a function of time. Okay, and I'm going to leave that typo in there because smart enough to know what I'm saying anyways. All right, so based on the information gathered, here's a summary of Microsoft's valuation from 2020 to 2024. So it shows significant growth, obviously, because they invested heavily in OpenAI and are benefiting from it greatly. It was a good decision. And we have a nice little citation here if we wanted to go see where it got the data from. And then it's saying, great, now it's writing a program for me to generate this plot that I requested. So not only can it deal with language as we canonically think of it, but programming is yet another language. In fact, it's easier than our language because it's highly constrained, and the syntax is very, very precise. So now it's generating the figure. And it's going to create the plot. And so this is, I don't know how many of you guys, maybe some of you, this is like, yeah, no big deal. I do this kind of stuff. Hopefully some of the rest of you think this is pretty impressive. And this isn't even dabbling into its vision capabilities, right? I mean, I can take a picture of I'm out at the beach. I'll take a picture of some beers on the table, and then I'll take a picture of my receipt, and then I'll say, how many of these beers cost me this much money? And then it'll like read the labels on the beers, and it'll read the receipt and find out how much it was and sum up how much the beers cost me out of the total receipt, right? So. Oh, wonderful. Wonderful. Good job. Performance anxiety GPT-4. All right. So we will skip this part of it here, but usually you just say something like try again, use matplotlib, use Python, and then you kind of give it a go, and then it'll usually succeed after a few more tries. But so this is the kind of stuff we're going to be talking about, is like, how are these operating and what's going on under the hood? All right, so intro to large language models. I figure what better than to use AI to help me describe itself. So this is an AI generated image, and I asked it to generate an image of an introduction to large language models, and this is apparently what it thinks is an introduction to large language models, according to Leonardo.ai. All right, so high level overview. We're going to start here, and then we'll kind of peel back the layers little by little. But there's kind of three aspects that I'd like for us to focus on. You've got the input, you've got the model itself, and you've got the output. The way these models work is they're an autoregressive model that is designed to model the probability of the tokens in sequence and then output the subsequent tokens. And we'll talk about what all these words mean in a minute. We're going to spend a lot of time looking at this input space and how we represent it and what it means. We won't spend too much time here. Although there's a lot of very interesting work under the hood regarding the computer science for optimizing, training things at scale, parallelizing with GPUs, probably not super relevant to this audience, but we'll take a peek at the few aspects of it that I think are necessary or that are relevant to what you're interested in. And then we'll talk a little bit about the output, okay? But in a nutshell, what you see here is the big picture. You've got a sequence of tokens, you put it in the model predicts the next token, you append that token to the input sequence, put it into the model predicts the next token, you append that token, and you iterate, okay? So we'll start pulling this apart little by little here. So I wanted to start just by stoking your intuition a little bit. Let's start off with the concept of 27, okay? So this concept is abstract in nature, and there are various ways for us to represent it. So let's maybe query the audience. Give me some common ways that you can think of how we as humans might represent the concept of this abstract notion of 27. The words 20 and then 7. Perfect. Nice orthographic representation of this abstract concept of 27. How else might we represent this concept? Equation. An equation, right? So maybe, yeah, sure, exactly. So numerical systems like Arabic numerals, right? What else? Cube of 3. Okay, more equations, exactly. Yeah, we can make it super elaborate. Yeah. 27 objects. Exactly. Spatially, right? This sort of maybe through space here. 27. Anything else? Quarter and 2 tenths. There we go. Exactly, right? So most of us know that while labeling, we are at risk of circumscribing reality within the confines of our own notions here. So I'm going to throw up a few categories that we may quibble over a little bit if we want to talk about what is orthographic, what is phonological, what is notational. But I'd like that we focus at the high level here, just in the notion of representing concepts, to just kind of stoke the intuition here. So
Orthographic, we heard one way to represent it orthographically. Acoustically, right? We didn't really talk about that representation. Phonetically, right? So is that different than acoustic, and what does that mean? And then others, right? So we have just straight up orthography as we think of it, Arabic numerals, maybe Roman numerals, or even binary. And what's important here is that why do there exist so many different representations, right? That's one of the fundamental things we want to think about. And the reason there exist numerous representations is because each different representation is amenable or useful in different contexts, right? The utility, like which one's better or worse than other, that question doesn't make sense in a vacuum. It only makes sense relative to some task or some functional objective. For example, Arabic numerals, 27, that's useful if we're going to do arithmetic and we want to do our algorithm 27 plus 55 and we're going to write it out, right? Or binary, if we're going to multiply by 2, binary is great. Left shift, put a 0 in front of it, you've now got 2 times that number. Roman numerals, yeah, they're great if you like Super Bowls, I guess. Other than that, who knows? You have an acoustic representation, right? Or maybe we sample this acoustic representation and we get a whole sequence of numbers, right? This is also another useful representation of 27. Or maybe we go a step further and do a Mel spectrogram decomposition. And then, of course, we've got IPA, SAMPA, or something even more maybe expressive in the phonetic space are phonetic feature vectors, such as the one that Dr. Cooper Borkenhagen proposed in his dissertation. Or you have spatial representation, as was pointed out, or even sign language, sort of a spatiotemporal representation, right, where you need subsequent representations one after the other. All right, so we're stoked. Our intuition is stoked about representation. So the question we ask ourselves now is, how do language models represent language? Okay, so there's various ways to do it, and we understand that all these different methods have relative merits. So what are the concepts involved in representing language for language models, and which ones do we choose and why? Let's start off with an example. Here's a little snippet from Pride and Prejudice, I think. Oh, said Lydia stoutly, I'm not afraid, for though I am the youngest, I'm the tallest. Okay, so how can we break this up into pieces that can be consumed by a language model? As one example, what if I just pass this into the tokenizer for the Text DaVinci 002 model, which came from OpenAI? This is the early versions of GPT-2. You'd get this type of a decomposition, where each color represents a single unit, right? That's a single element that the model thinks of when it tries to operate on the sentence, which means it has no idea that Y, O, U, and none of those, it sees none of that. It just sees a single element for each color. And that comes at a cost, right? And what happens is that each one of these tokens, as we call them, are represented by a single number. And this is what the model consumes, okay? So a large language model is a computer program that operates in binary numbers. So we need numbers for it to operate on them. And what we do is we take text in its abstract sense, we break it into pieces, and then the pieces that we break it into correspond to individual numbers, and then this is what the model consumes. So how do we break up text such that these models can perform optimally, right? And what does perform optimally even mean? So yeah, when we're thinking about large language models, many times people kind of sweep under the rug a little bit the tokenization process. And there are a lot of limitations and a lot of consequences of the capabilities of these models at scale that are directly dependent upon the tokens and the tokenization strategy, which we'll look at in a moment. So I think this is particularly relevant to linguists and reading researchers. So we'll take a look at what some of these are. So just as a brief example, before sort of this machine learning revolution or the deep learning revolution, many of the tokenization strategies were handcrafted. You've got the Penn tree bank or the Moses type of rule-based tokenization strategy, and they both have relative merits. So perhaps the Penn tree bank tokenization strategy makes more sense for do, for don't and aren't, because here you separate do and then are and then. Yet it seems like maybe the Moses tokenization strategy makes more sense for can't, because because you have the can, apostrophe T, yet neither seems to be quite what we might imagine for won't, okay? And this is just the tip of the iceberg, right? I mean, what about languages, right? If you have multiple languages, the tokenization strategies become very complex. For example, Mandarin and Cantonese. You have to use machine learning techniques to actually learn the optimal tokenization strategies. Okay, so we talked about representations. We see now that how we tokenize the language and break them into numbers is critical for how the models operate. So the questions we ask ourselves now is, what are the governing principles that we should keep in mind when we're determining the tokenization strategies? Let's explore this with the famous sentence, once more onto the breach, dear friends. As we've established, the quality measure for a representation really depends on what it is we're doing. So what we're going to do is we're going to ask ourselves what it is we're trying to accomplish, and that will allow us to compare these different tokenization strategies to see which ones are better or worse than others. So in the context of language models, because once again, remember the importance of these strategies is dependent upon what we're doing. There's two general sort of extremes. One is character level tokenization, where I could take that entire sentence once more under the breach and break it up into individual characters, okay? And what happens when we do this is that we get this really long sequence length to represent what's the content of the information inside of that sentence. And another extreme is to do word tokenization, where we actually break the entire sentence up into individual words, and we get a much more succinct sequence length when we're trying to operate on this. Before we go any further, does anybody have an intuition about which one may be better or worse than the other and what the relative trade-offs or considerations are when deciding between these strategies? Strategic question to take a drink of water.
Do you need more numbers for the second one? Need to use more numbers?
Very good. So in this approach, you can kind of tell, you get really big numbers, right? Because there's so many more words than there are characters. And so now we're starting to look at a trade-off between sequence length and vocabulary size, and what that means with regard to modeling, language modeling on a computer is important. Any other ideas?
Change the meaning or the frequency of the letter.
Yes. So I think you're hinting at maybe the fidelity, like the sensitivity to perturbations, right? Sort of an entropy consideration. Yeah, very, very important. Yep. Anything else? Yeah.
Isn't it entirely contingent on what you're predicting, assuming this defines a sort of input space? Or are you assuming that we're predicting next word, like language model, what the type of language model?
Yep, it is, as we said earlier, largely dependent upon the thing we're trying to do, right? So what is the language model trying to do? What is the purpose of the language model, right? If we're doing a task that requires information at the character level, maybe you should think about a character tokenization strategy, even at the expense of this ridiculously long sequence length. But there are other, I would say there may be a few other considerations like programming, implementation, hardware constraints, right? So maybe as scientists, we'd say, well, we'll just make the hardware because we'll make the hardware solve whatever we need to make it solve because we have the scientific question that needs to remain pure, right? But maybe that's not possible, right? So these are the things we want to look at. So in general, you have a trade-off between a very large sequence length, which gives you high fidelity in the model, right? So you can get very high resolution information, or you get lower resolution information, but the model can be a little bit faster and more accurate, faster and more precise in its predictions at that scale. So it's basically like an information theoretic trade-off. So I don't think there is an optimal solution, but from an information theoretic perspective, there sort of is the optimal coding theory approach. And I'm going to share with you now what's called the byte pair encoding algorithm, which is the current tokenization strategy that's used by GPT-4 and many of the large language models that are dominant right now.
Well, can you go back to the previous slide and just to be maybe a little bit more concrete for especially the students in the audience. So a comparison might be, so here, the kind of context of we're thinking about large language models, these very sophisticated engineering systems that can do the things, albeit with occasional error, like you showed at the start at the top. So you might, an alternative might be like Jeff Ellman in a classic paper he wrote in 1990 called Finding Structure in Time, used the most simple sequential processing models, SRNs, right? Which all it did was predict the next thing in the sequence over individual letters, which looks very much like what you're describing here. And this was, like 35 years ago now. And what he found in his architectures was that a model like that could determine the boundaries between words in connected text, even though the boundary between words is not explicitly marked, but just by virtue of extracting statistics associated with sequential words. But notice, like in that context, the prediction is very crude. Like you can't probe that SRN system to say something about the underlying meaning of the words or tell me how to, define a word or do something even far more sophisticated like the prompt that you generated at the start. So it just like thinking about the nature of the prediction problem, the nature of the representation, and the type of information that you can extract out of the computational model. These are all like deeply ingrained aspects of the problem that I think are really important to keep in mind in the context of these sophisticated models, but also in the context of more simple models.
Yeah, I mean, I completely agree. And we're going to be able to look at that a little bit more with one of the examples coming up, but it's always intrinsically a trade-off between what it is you're trying to accomplish. Like that's where the majority of the guidance comes from. Like is your actual question, as we said, a representation's value only makes sense in the context of some function or some task. And then the medium or the space with which this thing is supposed to be implemented, right? Our brain's highly parallelizable, and we have really efficient use of energy in our brain, and we can't quite do that with technology yet. So that's a constraint as well that we have to acknowledge also. But yeah, thank you for clarifying on that. That's a really important point. So what we're doing with byte pair encoding is we're taking the entire corpus that the model is going to learn from, and we're going to find an optimal tokenization, an information theoretic optimal tokenization strategy that gives us a balance between sequence length, but preserving enough information that the model can still do useful things. So just as an example, if we have this string, which is for now going to be our entire corpus for the sake of pedagogy here, the sequence length is 11, but the total vocabulary size is 4. There's 4 unique characters. So how does this algorithm work? Well, it says, I'm going to go through this entire sequence, and I'm going to find the most frequent co-occurring pair of tokens. And the idea is that since they occur so frequently, then maybe we don't need a whole lot of information to represent them, right? Just kind of information encoding theory. And so you identify that the most commonly occurring character, starting from left to right, there's a couple that tie, is A's, right? You have 1, 2, 3, 4. So 2 A's is the most commonly occurring pair of tokens. And so you forge a new token. You mint a new token out of thin air, which we just call Z for the sake of representation here. And what just happened now is that our sequence length got smaller, but our vocabulary size increased by 1. We created this new token. And we just keep going, right? So with this new token now, what happens? Well, the next most commonly occurring pair of characters is AB. We have AB, AB. And so we forge a new token, Y. And what happened there is the vocabulary size increased by 1, but the sequence length decreased again by 2, which is good. And then finally, we arrive at the end where there are no more pairs or byte pairs, as it's called in byte pair encoding algorithm. And we have the sort of byte pair encoding optimal tokenization strategy with the sequence length of 5 and a vocabulary size of 7. All right. This doesn't always work, and we're going to find out exactly why in just a moment. So let's take a peek here. Sure. No. Very good. So that was kind of what she was hinting at earlier, right? Is that if I use single words as the fundamental building block of my entire ability to reason in language, I'm going to have over 170 something thousand unique elements that I need to memorize and figure out how they fit together. But if I use characters as the fundamental building block, ignoring punctuations and special characters and capitalizations or whatever, you need a few dozen, 20, 26 if you deal with, no capitals or anything, right? So the vocabulary size is the total number of unique tokens in the entire space of things being considered. That make sense? Yeah. And so here, the total number of unique tokens is just 4. Yeah, perfect. That's a very good question. All right, so let's take a look. So what we have here is the GPT-2 tokenizer. This is the same tokenizer that they're using for GPT 3.5 and GPT 4. Let's just take a look at one of the things that happened during the byte pair encoding algorithm. And let's start from the top, right? So the number 11115, 11116, 11117, they seem to have a similar structure, right? Where it breaks into 2 ones and then 3 numbers, 2 ones, 3 numbers. And we keep walking down, and then suddenly, what the heck happened here? All of a sudden, for 1111 or 11,119, it just decomposed that into a different sequence of tokens. This is one of many reasons that large language models are not particularly good at arithmetic. They have a very mixed foundational representation of numbers. And so if I were to give it an arithmetic problem, it might represent numbers in weird different ways that make it difficult for it to tease apart the fundamental patterns that govern how numbers work together, or at least the way that we use our numbering system. Okay? This is a pretty important thing, is that the tokenization strategy, I mean, these are, as I said, they're the linguistic primitives. They're the semantic building blocks of these models. And if this is not precise, then anything that it does on top of this representation is just fundamentally limited by the information content in this representation. Yeah, go ahead.
Do the colors here have that same kind of key that the colors had in the one where you had the words and the letters?
No, they're just used for delineating boundaries for now. If you notice, this and this are the exact same token, yet they have different numbers. So 1157, I'm sorry, they have the same numbers, right? So it should be 1157. Oh, there's a new line. Sorry, there's a new line hiding. That's why that's confusing. So there's 3 tokens here: 1157, 15363, 198, and then 1157 again, right? So this 11 is the exact same token, yet they have different colors. It's just for visualization to delineate the tokens that are broken up. Very good. Yep.
By point of comparison, it's worthwhile to think about how a middle schooler might tokenize here based on their pre-existing knowledge, in contrast to how a machine does it, and the types of developmental factors that go into child knowledge development about math that would underlie their tokenization process by comparison, which would be very different.
Do you have an analogy for us? Because I don't deal with it.
Middle schooler might use place value, for example, in order to decompose the sort of constituent parts of numbers of this type. Or they might build it from the Arabic numerals themselves, right? And so that sort of process of chunking the tokens, which is look very different.
Yeah. And the ability to even do that requires that you have at least an individual number representation in your mind to group them in arbitrary different ways. That process, exactly, that process he just described is fundamentally impossible in large language models because it just doesn't have a high enough resolution to understand numbers the way that we do, right? Or to put it more precisely, the model also has the representations of individual numbers, right? So, I mean, if I can come here and add 1, right? 2, 3, 4, it has the representation of individual numbers, but it doesn't consistently decompose sequences of numbers into that pattern. So while it has the capability, it's not robust. It's not baked into its fundamental reasoning strategies.
So one could imagine training a machine system using data sets that are coherent with what children experience, and considerations about the structure of the model and its growth over time that's consistent with what we know about child development. And this science is done, but it's a, a sort of alternative approach.
Absolutely. And we might be going in that direction with a couple more slides here. We'll find out. Yeah.
So question on this. So we're visualizing GPT-2's, like it's already tokenized based on some training set, and then we're
The
just
byte pair
studying-
encoding algorithm.
Okay, yeah, because this isn't quite the same as your previous example where you generated the tokens based on frequency of occurrence and stuff.
No, this is the same. That's what I'm saying.
Okay,
So
yeah.
what
But
I should,
but it's not just like training on the stuff on the left to make the stuff on the right. It's
No.
using like a
correct.
pre-trained tokenizer.
Exactly. So what they did is they took Wikipedia, the Common Crawl data sets, internet data from all over the internet, which I'm going to show you in a minute is a problem, and we'll see exactly why. And they applied the byte pair encoding algorithm to just terabytes of data, right, across the entire internet. And this is the byte pair encoding optimal tokenization strategy that emerged from that. Yeah, exactly. And you can, play with all these other different types of embedding, encoding strategies that have been from different models over time. You'll see that most of them are pretty consistent with the GPT-2 tokenization strategy. This one is, notice this one is a little bit more reliable and didn't have that same mistake. So here it consistently has the 3 first digits and then well, at least for these numbers. If I went to 30 or 40, who knows? Maybe it would randomly make another mistake again, right? So yeah, good question. And then when you go to GPT-4, it gives you even more like price estimates, et cetera. And these types of tokens that we're seeing here are, you notice that it uses this entire string as a single token. And these are how it starts controlling the model for conversation and getting it to accomplish tasks, which is where we're going to get to in a minute. But before we do, let's take a look at something else very interesting. So let's do something like this. Like, what if I just wanted to represent, I don't know, someone's name like David? Well, that didn't work, right? Why doesn't it have a name as a single token? That's a pretty common name. Or even more interestingly, what if I just start putting like random letters after it, like KL? Oh, okay. Or what if I did like OL? No. But what if I did JL? No, that didn't do anything. What if I put a space in front of it? What the heck just happened? For some strange reason, there's this single token space David JL that the byte pair encoding algorithm decided is like super important that all of these characters be chunked together, right? Why and how did that happen? Well, that happened, interestingly, because David JL123 is a user on Reddit who was a very prolific poster and happened to dominate a very large portion of the training sets that these models were running their algorithms on, such that he received the award of becoming a single token in the GPT-2 tokenizer. But this comes at a cost. This token is so useless at language that the actual representation inside of the model, the gradients pushed the embedding vector to basically 0. So let's watch what happens, right? So let's go to GPT. We'll grab a new one here. Let's use 3.5. It's a little more reliable. And then I can say something like, what does space David JL mean? JavaDoc typically refers to, that's not what I asked, right? I can modify this and maybe make it KL. And as you saw, it accurately decomposes this into the proper tokens. David KL, it knows what that means, right? I can come in here and, delete the K, David L. What does David L mean? It says, again, without additional context, David L could refer to anything, but this weird magic, what is called glitch token, just breaks the model. It has no internal representation of, JL, sorry. It has no internal reliable representation of this token internally, right? JavaDoc, maybe it says something else. If I rerun it, it'll just guess something else oftentimes, JTL something, JDK, right? It can't figure out what that token means. It never learned it. Yeah.
So the other ChatGPT that's being the tick tokenizer, that is kind of like the R code of ChatGPT.
The what? I'm sorry?
Like the R code, like where you're putting in your script in the code for ChatGPT.
No, this is just an interface that allows us to see how text is tokenized by different tokenizers.
Oh.
And then once the text has been tokenized like this, the model consumes this sequence of numbers at the bottom, right?
This is where the text gets transformed into the numbers to give us the output of.
You got it. This is just an application that gives us visual insight into what's happening under the hood with all large language models. Very good. Yep. So one other important thing, we noticed that models, large language models, GPT-4 in particular, are very good at programming and coding. So much so that OpenAI, on their iteration from GPT 3.5 to GPT-4, made some explicit modifications to their tokenization strategies to allow their models to be even better. So we can take a quick peek at OpenAI's tokenizer. All right, so this is another tokenizer application offered by OpenAI itself, and you can see, again, the tokens, the characters, the uniqueness here. So I wrote a small, silly, literally useless program just so we can see how it's tokenized down here. So this is GPT-3, right? This is the same tokenizer as was used in GPT-2. But when they went to 3.5 and 4 in Turbo, they made some modifications to the token strategies so that it actually took into consideration the indentation structure of Python so that it can represent programs more efficiently, it can have longer sequence lengths, and it can just be better at programming in general. Okay, so these are just numerous examples that I'm hoping can drive home how profoundly important I think the tokenization strategy is in determining the bounds, the limitations of what these models can do once they start consuming text. All right, are there any other questions on this stuff? All right, let's continue. So we saw, okay, we've got a bunch of words, they go into a model, and then it predicts the next word, or tokens, get tokens, they go into a model, predicts the next tokens, and we churn. What is the objective? Like, what are we doing, and what does that box in the middle have inside of it? Okay, so let's just assume we have 3 random words, and I'm just gonna randomly sample words from the internet. Matt has smelly, that was weird. Yeah, so we have 3 random words here, and we're gonna try and create a modeling objective now to understand the statistical frequency with which these tokens co-occur with one another. So firstly, we'll assign a variable to each one. And remember, there's numerous tokenization strategies as we established. Here, we're just going to focus on word tokenization for simplicity. So this isn't how it's done, and this isn't how we want to think about it in practice. But for the sake of learning, we're just going to use word tokenization. So the question is, what is this? This is what we want. What is the probability distribution over all tokens in the entire vocabulary? Because if we have this, if we have the full data generating joint distribution, we can describe everything. All right, this is kind of the holy grail in statistical learning theory. If you learn the data generating distribution with Bayes theory, conditional marginalizations, you can calculate anything else that you want. Okay, so in particular, we can just decompose this into this formula. And this is, each one of these is the large language model, right? This is the large language model operating one step at a time. So remember, we have what's the probability of the subsequent token given the ones that preceded it. It predicts that token, takes it, appends it, and then it predicts what's the probability of the next token given the ones that preceded it. It predicts whatever that is, appends it, and continues and churns along. So the learning objective is maximizing the probability of each of these conditional distributions.
Also address the issue of morpheme, like would it separate smell from wine?
I am under the impression that that is a function of the tokenization strategy. So whether smell is separated from, smelling, smelled, past tense, or smelly, that depends on the statistical frequency with which those words show up and how whether byte pair encoding breaks them apart enough to happen, which, by the way, yeah, I was about to say, it does oftentimes. So we can do things like running. Okay, that one gets a single token. But if we do, some of them are broken up. Jump, okay, that's weird. Yep. So we can go to GPT-4, take a peek here. So there we go. GPT-4's tokenizer is a little more expected. We can do smelly. Weird. But maybe SM shows up so much more frequently that the model that byte pair encoding suggests that it's useful to have an individual token representing SM rather than for the entire word itself. Yeah. Yeah, great question. Yeah. All right, so with text, as complex as it is, and as fuzzy as all of the syntax is that we use it with the multiple meanings of words and as they evolve over time, we need a whole lot of data to try and tease apart this really high dimensional complex data generating distribution. So for example, if we used a word tokenizer, we would have, at least 171,000 elements in the vocabulary. If we used a character tokenizer, and this is an interesting thing, which we'll talk about in just a moment, we could have up to 144,000 tokens if we used Unicode's representation, or 14.0. I know we're like 15 something now. I couldn't find that number. Or if we used WordPiece tokenizer, which is used by BERT, which was one of Google's models that began this revolution a long time ago, we'd have 119,000. And byte pair encoding has a little over 100,000. Earlier, though, I said character tokenization was great because it had smaller vocabularies. So why does this one have so many more? Any ideas?
Maybe counted the parts of speech. No, this is very.
Not in this one. No, that's a good guess. Any others?
Does it take like frequently occurring 2 or 3 characters together and make them a unique one so that it's also part of the corpus?
No. Good guess.
Recognize like I am and I mean the same thing. One cannot and can't.
Nope, because it's at the character level. So the reason is because this is currently representing any possible character that can be on a computer. I mean, I'm talking like integral signs or foreign languages or weird emojis. I mean, this has every possible character that Unicode represents is captured in this vocabulary. This is a very active area of research. People want to find ways to allow large, it's called tokenization-free modeling, right? Where it just operates on Unicode, which is going to be pedantic, a form of tokenization, but it's like so fundamental to everything we have. It's the individual units that the model could use to operate on, but the sequence lengths are too long, there's too much memory, and we can't operate fast enough to do that effectively yet. But that's a good area to look into. Yeah. So that's an interesting question. And I had a chat with a colleague about a year ago where I said one of the ways that we could fix some of these problems with models not being able to learn how to break apart numbers correctly is, even though the tokenizer traditionally breaks up 119 or 111,119 into those two tokens, what if periodically during the training process, I just forced a character-based tokenization using the individual characters that are already in the vocabulary? Because that full vocabulary also contains individual characters. We saw that, but the model just chose to tokenize in a different way based off the statistics of the byte pair encoding algorithm. So what if during training, we just forced it to use the characters periodically to help the model actually learn representations internally that are more fundamental? So I think it's a very insightful question, and that'd probably be an interesting thing. I hope someone does it someday. Maybe you should look into that. Yeah.
I think it's worthwhile for a moment, especially given that the talk is hosted by a Center for Reading Research, to dwell on the fact that the types of probabilities that you're talking about calculating are calculated over text. And if you're interested in understanding reading behavior, what are other aspects of the language that might come into consideration if you want to know something about the probabilities of an element given its context beyond just the text? Because we know more than just orthography is involved in reading.
I suppose you're hinting at punctuations at a minimum, right?
Yeah, we love punctuation. Like thinking about how phonology contributes to these types of cognitive processes in humans, semantics.
It's almost like my talk or something, because we're going to go and do that in just a moment here. Very good. Yeah. Okay, but before we go to that very important point, I said we pulled pull the curtains back a little bit. So I'm just going to give us a flow of what we saw before, but with a little more detail. Okay. So here's a sentence. Ichabod likes headless horsemen. And we're going to pass this through a large language model. Okay. A semi-large language model, Phi 1.5, which is actually really small. But so using Phi 1.5, which came from Microsoft recently, this is its tokenization strategy for this sentence. Right? We see somewhat reasonable decomposition of compound words, horsemen, headless. Also, curiously, or maybe not curiously, Ichabod is just chopped up into all kinds of tokens because it's such an infrequent word, right? That it doesn't really, it's not preserving valuable information by keeping that whole thing as a single token. Yeah. So we get the sequence of numbers. Okay, now we stopped here before, but what happens next? Okay, what happens next is that each of these numbers correspond to a row in an embedding matrix. So what that means is that every token inside the model is represented by a single high dimensional vector. So some point in really high dimensional space is how these models think about these tokens. And that's important and useful because any single token can have multiple dimensions that it can be expressed with, right? It has multiple meanings. And if this single token are represented with a single number, I'm trying to pack all of the subjective fuzzy information associated with the single token into one number. And that's just not a good thing to do. So we need a more high dimensional, more complex way to represent the fuzziness and subjectivity of how we use language. And so each token is represented by a high dimensional vector, and each dimension can capture different information about that word or that token. Okay, so that's what happens is we come here and every token just plucks a row out of this embedding matrix, and then we get this giant input tensor, and this is what goes into the large language model finally. Okay. So here we sweep the details under the rug. You've got the transformer, self-attention, cross-attention, cool stuff going on inside of here. We won't dig into that. But I did want to emphasize one thing, that with all the complexity and the really important computational innovations that have been developed for large language models, at the end of the day, for you, it's simply a ridiculously over-parameterized categorical distribution. It's what it is, right? You give it a sequence of tokens, and it outputs a vector of probabilities, which is a categorical distribution. And this is a distribution over tokens. And it just says which token is most likely to come next, given everything else that preceded it. That's a categorical distribution. So conceptually, these large language models, gigabytes of memory running across multiple GPUs is just a very highly parameterized categorical distribution. Now I ask you, given this categorical distribution, what do we do? How do we choose which token comes next? Maybe. That's called the greedy sampling strategy. But is that what you want? Maybe not always, right? You might have heard of things like top P or top K, right? And so they give you ways of sort of plucking out the most probable next tokens and then maybe sampling from them in a constrained way that introduces a little stochasticity, which actually models the way we use language a little bit more reliably. Yeah. So you can do greedy sampling, and it makes sense, and it works, but you get into weird patterns with greedy sampling. Like suddenly you'll get into a loop, and it'll just predict the same token over and over and over again. And interestingly enough, injecting a little bit of stochasticity into how we sample from the categorical distribution allows the models to operate better. And then even more interestingly, which we won't do here, do we do that during training or do we do that during inference, right? Sure, yeah. So kind of the seminal paper that demonstrated this is a really promising direction to go. You probably heard of it, like word to vec. You guys heard of that concept, right? So what happened there is you basically just said, I'm going to try and come up with a way of representing each of these tokens or words or whatever we want in a high dimensional space such that I'm capturing intrinsic statistics about how these words co-occur with one another. And with that learning objective alone, there's enough information to tease apart semantic relationships in that space. You've probably seen you can do man plus king is equal to like woman plus queen or things like that, right? So it starts understanding intrinsic semantic information. Now, why? That's actually what we're going to get to in just a minute. So I think you'll see the answer in just a second. Yeah, good question. Yeah.
Just because they're
Nobody really uses those anymore. Yeah, I mean, if you want embeddings for words and tokens, I would just go to the cutting edge embedding. You've got the Google Universal Sentence Encoder, you've got the ADA embedding model from OpenAI. And these operate at a much larger scale on terabytes of data. And so the semantic vectors have much more information. Not only that, but you can learn semantic vectors at multiple resolutions. You can get embedding vectors for individual tokens and words, or you can train it to learn embeddings at the sentence level or at the paragraph level. And it's learning different characteristics at these different hierarchies. So there are more precise tools for what you're looking for, most likely.
If I could like reframe it, and correct me if I'm wrong, but it's like an input vector of numbers, and in a way, you're just kind of multiplying it through a series of matrices, and then you get an output vector, and that's like the probability of your next word. So yeah, he's using words like these high dimensional spaces. In reality, I mean, that's not incorrect, but in reality, yeah, it's just like a giant matrix of numbers. And those numbers have all these intrinsic meanings that have been built up. But yeah, like one simpler way of thinking about it is just like take some numbers, multiply it into your matrix, you get an output, and multiply it into another matrix, get an output, and just like pass it through a series of multiplications, and then there's your output numbers, and the output numbers have that meaning associated with it, and then the value is like the probability.
That's an equivalent way of saying it. Yeah.
I have a question about the embedding matrix. From the demonstration earlier, it's clear that the mappings between the numbers and the tokens is like entirely arbitrary. But does it matter numerically, for numerically similar tokens? Does that matter in terms of how they become represented? Are they naturally, is the disposition to represent them as more similar just by virtue of the tokenization value that's attached to it, which itself is arbitrary?
That's a really important detail. So a common approach used to be what everyone's probably heard of as one-hot vectors. One-hot vectors are basically the maximum entropy assumption, right? It's the prior, the uniform prior. You're basically saying, I know nothing about these, and I'm going to bake in zero information into their representation, and I'm going to allow the model to learn how to represent these things. That's an important approach. However, that does bake in an assumption, and that's that everything is maximally dissimilar, right? If you have these one-hot vectors, that means every word is represented at the vertex of this really big high-dimensional hypercube. And that makes it difficult for the model to learn how to move these points to places in this high-dimensional space such that they're semantically similar or related to one another. So what people have been doing lately is they actually randomly initialize that embedding matrix, and the embeddings are learned during training. Okay, so every one of these rows, they're randomly initialized. So you got a bunch of points that are distributed in a big Gaussian cloud, like this big cloud in high-dimensional space. And then where those points are in that space move around based on what's useful for solving tasks downstream. And then just in the way that word2vec or glove, where the semantic information emerges, that also happens in training when you learn the embeddings as a function of training.
Okay, but does that mean though that without that learning constraint, the learning of the embeddings, that the numerical method is equivalent to one-hot encoding where the number is just the hot node?
Yes.
Okay, that's the same thing.
Yep.
Okay, so that means numbers that are similar to each other are not by nature similar unless their similarity is learned.
Precisely. Yeah. And to Justin's point, right? If you have a matrix and you multiply it by a vector, what is matrix vector multiplication? That's a projection of a point onto a subspace, right? So that's literally what you're doing, right? Is so you have some really high dimensional space, you have a point, you multiply it by a matrix, you're just projecting it onto some smaller subspace, depending on how many columns you have in your matrix. So what these models are doing is you start on this really high dimensional space, and you're just consistently projecting points onto subspaces within subspaces. And these subspaces are containing really useful and interesting semantic information, and it's teasing apart like fundamental properties of language. Certain attention heads are learning nouns, certain attention heads are learning the process of conjugations, and that's been observed. So yeah, I think that's a really important point to look into. So greedy sampling, whatever type of sampling we want, as you saw, we get the token, we append it to the sequence, and then we pass it in again. So in this scenario, the period had the highest probability. We sampled it, we appended it to the sequence, so we pass it through the model again, and we just keep churning. And I just want to emphasize once again how similar this is to what we talked about in the beginning, right? This LLM is this box. That sentence up there is our sequence. And, well, I guess this part right here is our output. But we added a little bit more of the information, right? We have the tokenization strategy. We tease out the embedding vectors. We put them into this input tensor. And then we do all the cross-attention, normalization, everything inside of the large language model. And then we get our output categorical distribution over tokens, which we sample from and we churn. So I think this is a good way to have an intuitive understanding of what these models are doing without needing to get into all the technical idiosyncrasies of the LLM itself. Yeah.
You call this a small, like, is that like trained on a small corpus, or is that what makes something small?
It's small because of how many parameters it has. So Phi 1.5 has about 1 billion parameters. But for example, GPT-4, nobody knows, but allegedly it has over 1 trillion parameters, right? So GPT 3.5, the published paper, they have 175 billion parameters. The Llama models, they have 7 billion parameters, 13 billion, 35, 70 billion. So these are the scales of what we consider to be large language models. But Phi has only 1 billion parameters, like 1.2 or something. Yet it's almost as performant as some of the models bigger, which was what Microsoft was trying to get across. They're like, we can actually use smaller models, but use better data sets and get models that perform pretty well.
And then when you say parameters, it's like the size of these matrices that you're diving into, right?
Sorry, yeah,
And
exactly.
then those numbers are meaningful to train.
Yeah, this box right here. How many numbers are in this box, basically? How many matrices are in that box? Yeah. Okay, so why does this work, to your question? Largely, it's the distributional hypothesis, which many of you may have heard of. It sounds like something more relevant to the reading research field. It's kind of a 1954 idea. So the fundamental definition is that words that occur in the same context tend to have similar meanings. Okay, so we're going to do an experiment to show how this works live with all of you right now. So we're going to learn what this word means. Have any of you ever seen that word before? You haven't, because I made it up. So we're going to learn what this non-word means using the distributional hypothesis. So it's a game. So one of you is going to win, and that's going to be whichever one of you is able to guess the correct definition first. Okay? And I'm not going to tell you the rules. You're just going to figure it out by virtue of the distributional hypothesis. Once you know the definition of this word, say it out loud. That was fast. We didn't even need multiple examples. Yep. How did we know? Right? I'm sorry?
Is it passion or motivation?
Well, let's find out. Is it passion or motivation?
Passion.
Oops, I'm missing a word there. Okay. We can argue, maybe it's motivation. I intended for it to be passion. Like I created these, I asked actually GPT-4, give me 5 sentences with the word passion in it. I just took them. So all we needed to see was the co-occurrence of words to figure out what another word means. And so the significance is that this concept underpins those token embeddings, those vectors. And then what happens inside large language models, there's lots of vector-vector multiplication, which you guys know is like cosine similarity, right? You can measure how similar two vectors are in a high dimensional space by taking their inner product. Well, that's what these models are doing internally. over and over and over again. They're measuring the similarity of all these tokens and when they co-occur next to one another, and it pays attention or tends to different tokens that are within certain distances of other tokens. So this is kind of the driving principle behind why and how we think these models are able to be as effective as they are. I think this is a really important concept, so I've tried to come up with a pithy little way of remembering it, inspired by good old Hebb and his neurons that fire together, wire together to help with the neuron doctrine and Hebbian plasticity. So words that flock together, talk together, if you want to try and remember this principle. Yeah.
In the previous slide, we saw that the output that comes out of the LLMs, which are like probability distribution for each, that may be the next word. And you said we can either choose like the topmost highest probability, or you could choose like a top K. So let's say, for example, if I want to finish up any one of the sentence, and I take the top 5 probabilities, and if I try to fit in all the 5, how does the model know that which gives the better contextual accurate answer for this?
So let me make sure to say it back to you before I answer. Assume you take the top 5, you sample from it, and the one you take is not the most probable. How does the model know what exactly?
Contextually in this way, because we, as you said, the more the number of training samples that we give with the proper context.
Yeah. Because what does it mean contextually to be right? The point is that the reason the model is uncertain is because that we use these words in unreliable ways. Like certain words will occur after other words with probabilities. So the dog jumped over there's not a single answer there. There's no correct answer there. So when we sample from it, I would say that that's an ill-posed question, right? Well, there is no correct answer. There's just more correct answers, which is why it's probabilistic in the first place, right? Yeah, but that's an important idiosyncrasy to work out. Yeah. Good question. Okay, so let's do this pretty quickly, and then we'll talk about some interesting work. Once again, I asked AI, what is the evolution of large language models? This is what it happens to think that looks like for whatever reason. All right, so transfer learning. Here's my fun little just cartoon to stoke, to help you understand transfer learning, and then we'll talk about it technically. So this is McGlorbaglorb, all right, and so they're visiting us here, and then Sally and McGlorbaglorb are hanging out, and then they're just looking at a scene somewhere, and then McGlorbaglorb says, "Hey, what is that red thing?" Somehow it knows our language, but not what a car is. We'll ignore that detail. And Sally responds with, "It's a car, and we use it for transportation." So assuming McGlorbaglorb has eyes and processes information in a neurologically equivalent way to us, they are creating an internal hierarchy of information from the back of the cortex working its way forward, little lines and edges, which are assembled in ways that give us a more complex and sophisticated representation of information. And so what happens right here is that she gave a label that said it's a car. And so what happened is, in neuroscience, we call it the credit assignment problem, basically, which is car gets assigned to this complex object, yet somehow this cascade of neural activity where all these individual shapes were contributing to this larger representation must also inherit some proportion of that label, right? So wheel somehow is a part of what a car is, and it inherits a bit of that label car, right? And when that happens, we are able to reuse these fundamental representations of more complex objects to do other things. So McGlorbaglorb, being a really smart alien, is walking around and looks at this and decomposes it in its mind using the same process as us, allegedly. And it says, hey, is that also used for transportation? Because wheel and line or bar, wheel and line and bar inherited this proportion or this a certain amount of carness to them, and now it's being repurposed because the semantic notion of transportation is assigned to the label car, and so it's saying, hey, maybe this is also used for transportation. So this is kind of a cartoony, silly way to understand the idea of transfer learning, is taking information that was assigned to something in a complex hierarchical way and then transferring aspects of it to solve other tasks in a generalized way. So yeah, we call it a bike. And now bike and car, so wheel has just become a more robust representation of transportation. Now has wheel and car, right? All right. So how do we do this in machine learning? Well, 2018 was the first paper that really drove this home. They demonstrated that we can do what's called fine tuning. So let's just talk about that briefly. This is a large language model, input, your box, your output. Ignore the details, it doesn't matter. You do one path of training from the bottom out to the left, text prediction. And you do that over and over and over again on so much data, terabytes of data. And the model starts to learn the intrinsic statistics of these tokens and how they co-occur with one another in ways that are useful for solving downstream tasks. So first, you just train the model on language and you say, predict the next token, predict the next token, predict the next token. And you do that over and over and over. Then it turns out that once that has been done, you can take that model with all of those weights and all of the semantic information that it extracted and that it learned about those tokens. And then you can train it again, but just for a few epochs. You don't need to train it nearly as long, like literally 1,000th of the amount of compute that was needed for pre-training, which is that process you use for fine tuning. And it can do all kinds of other downstream tasks. Classification, entailment, logical entailment. Does this conclusion, is this conclusion entailed from the predicate? Similarity, sentence similarity, which usually gives embeddings for sentences, multiple choice questions, and reading comprehension. And each of those tasks can be solved with a very limited amount of training, given the pre-training that took place. How? Transfer learning. The intrinsic statistics or the internal representation that the model learned about all those tokens are useful in many of these tasks. All right, so that's fine tuning. So what happened after that is people observed this thing called in-context learning. So what happens in context learning is, oh, actually, let me just show you.
I have a question. So for fine tuning, is that another form of training the model, but now you're trying out these different contexts, but then is that then feeding back and altering the parameter space?
Yep. You are updating the parameters during fine tuning, but the point is that pre-training takes millions of dollars, weeks of training on hundreds, thousands of GPUs, and fine tuning takes a weekend on a couple dozen GPUs. And that's because it's able to learn new tasks very quickly by transferring the knowledge that it learned from the general statistics of how language is used across everything that it saw.
Okay, so you know, so maybe like another 3 meetings, then I can proceed because there is another meeting here to say, so we go.
Okay. Well, then let me jump to the good stuff then. So we'll skip that section. So well, let me jump to the conclusion here, and then we'll go to our research. So what has happened is we started by observing that you can fine tune these models, right? So that's A. And then B is you learned that you can actually do this notion of in-context learning, which I didn't show you. But in a nutshell, what that means is that if you give the model a sentence and you ask it to predict the next token, it's just the world. It's the world's most glorified auto-completion tool, right? It doesn't have this conversational capability that we're used to. Where does that come from, right? That's nowhere in the training objective. How did that happen? Well, that happened because it turned out that if in the context that you give it, you actually give it examples of the questions you want it to solve. You're like, what's the capital of Florida? Tallahassee. What's the capital of Paris? France. Then you go, what's the capital of Japan? Question mark. It'll go Tokyo, because it's following the pattern. So it's learning tasks in the context. So you don't even need to fine tune anymore. That's the beauty of in-context learning, is you're accomplishing the same thing, but in the context of the prompt. So it's actually learning to solve tasks based off of the patterns that it's seeing in the sequence you give it. And then finally, someone was like, well, wait a minute. What if we just fine-tuned it on instructions, like on question answering, right? So first you did fine-tuning, which was cool. Then you did in-context learning. And you're like, well, why don't we just put them together and we do what's called instruction fine-tuning? And so the model learns to have a conversation, which is actually kind of interesting when you think about it, because children, as they're developing, they're just learning patterns of language, and they're like, hang on, mommy, daddy's talking. Give me a minute. They haven't learned conversation. That's a very social thing, right? The statistics of language and the patterns of conversation are just, they're pretty different. And that's kind of emulated here, right? The pre-training gives the model the statistical underpinnings of language, and then the instruction fine-tuning allows it to understand the patterns of conversation and how that works together.
So, because we actually discussed here that does this have anything to do with the type of prompt that we give to, for example, ChatGPT or GPT-4, does it impact their output? Is this part of the reason why prompt engineering, the way you interact with
Absolutely.
others,
Yeah.
affect the answers
Just
that they are
in a nutshell, we can't go into it, but if you, let me just grab another one here. Add message. So you see all these weird tokens in here, start, end, separator, end, start. These are tokens that are put into the vocabulary that the model uses to learn who's talking and when they're talking. So they're sort of baking it into the intrinsic training paradigm of how you pre-train models. So yeah, prompt engineering and when and where the tokens appear are really important. All right, so let's get to the good stuff just in time for Matt to leave.
You'll report it well.
Yeah, so here's our research that Dr. Matt Cooper-Borkenhagen helped so much with. Thank you, guys.
Yeah.
So with that underpinning, we're just going to look briefly now at what we put together. And again, this is transformer-based cognitive reading model. Apparently, this is what AI thinks that looks like. It's pretty good. So this is based largely on the triangle model work. We started by re-implementing the triangle model with neural differential equations, and we got some pretty encouraging results. And we're like, well, why don't we just use some more modern ML techniques and see what happens to these models? So this is what we created. This is our cognitive reading model. And there's a couple of important fundamental design decisions that went into this. The first is that it's multimodal. Well, sort of multimodal, because technically the phonological representation is orthographic encoding of phonology. So it's really both orthography, but we won't arm wrestle over that. So it is able to ingest orthography in the sort of canonical sense that we understand it, and a phonological representation of whatever the orthographic input is. This goes into two transformer modules, which we'll not worry about. And what matters is that they get compressed into a single hidden layer, which is inspired by some of the emerging neuroscience research showing how all these multimodalities eventually mix together in some sort of mixed complex representation that then get teased apart again to give us more robust representations of what it is we're processing. So this is a very interesting space that we want to explore. And here's the key constraint, is that this vector, which encodes both orthographic and phonetic information, must be sufficient to uniquely decode the original orthography and the original phonology, the phonetic representation. If the model is able to learn to do that, then this space is somehow mixing together orthography and phonology in a, well, hopefully interesting way. Or maybe not. Maybe it just partitions the space into two and solves them separately. I mean, we're still working on figuring that out. But this is the architecture of the model. One idiosyncrasy, though, is that the phonology, we're actually using Matt's phonetic feature vectors. So these are 30-dimensional vectors where each index is indicating the presence of the shape of them, like glottal, fricative, the position of the tongue, whether it's primary, secondary stress, airflow, etc. So it's a more robust way of, it's more phonetic in nature than just sort of an orthographic encoding of phonology, right?
Don't worry about it.
It's
Some
done.
letters don't have phonology though, so you can see how like the E is not represented because like above. There's no phonology of silence.
Yeah, it's learning to not say it because it sees the orthography and learns that, well, actually what it's probably learning is that even though it's silent, it may influence the pronunciation of other phonemes, and it's probably finding those patterns, yeah.
For silent letters, peculiarity of the English conventions of spelling. I don't know, it's a whole layer of things that, because it doesn't follow rules when you have a silent.
Yeah.
Unlike the E in a final position. Depends, there are rules for that.
Yeah, that's an excellent question. These are the things that we want to explore more of. Thank you, yeah.
Yeah, so it seems like the phonology is kind of the new bit here, right? Compared to the other models. Is that, are you like leveraging an existing model and then you're plugging in the interesting phonological breakdown and then that's part of this project, or are you like retraining a thing from scratch to be more like neurally plausible or something like that?
Yeah, very good question. So our task is spelling, which means which tokenizer do we need?
There's English by nature. So some of the spelling that sound irregular or so knowing the etymology of the name will also help. But maybe because I'm very interested.
I would argue, without knowing a whole lot about this, that those types of rules are things that we impose on language, which the model itself would learn from the data itself. I mean, in my opinion, but I think that's a really important question.
So just to clarify, previous model already have this phonology, maybe not as well defined as maths ones, but I think the thing that is novel here is the architecture, right? of the
Yeah.
model
So that's what I was
compared to previous.
exactly. That's what I was going to get to, is that we have to use a character-based tokenizer, which we created ourselves because it needs to learn to spell. And this architecture is we coded it up from scratch, right? So we just re-implemented the attention, multi-head attention heads. We concatenate the vectors using a global embedding vector technique where you append it on, et cetera. So the whole architecture is randomly initialized, and we train the whole thing from scratch on various reading programs, which is where we get to some of our results. So here's how quickly the model learns with different types of reading programs, because we want to see if certain programs are more effective than others at helping people learn to read. So here, this is all very preliminary, but it looks like decodable texts. The model is able to learn much more quickly, largely because the text is structured and it sees things that it should in principle already know how to pronounce. Random adult words and random child words. Random just does pretty poorly, but strategically sampled words does a little bit better. Also, we find that it does well on words that have a short number of phonemes and poor on words that have a large number of phonemes, which is consistent with behavior. Here is when the model learns each of the words in the Woodcock-Johnson 3 test. So in the bottom left here, these are traditionally short, easy words. And over here are traditionally long, complex words. And this axis is when the model learns it, which epoch of training. And so we see it learns all the short, easy words first, and then there's some discontinuity here where suddenly it just stops, and then it takes multiple epochs for it to start teasing apart the more complex words that have more idiosyncratic phonetic representations. And this is pretty encouraging results. Matt likes this a lot. This axis here, so each point is a word, and that word has two numbers associated with it. The number on this axis is how long it takes a human to begin pronouncing that word after seeing it. Okay, so I think in your space, that's just naming latency, right? And then on this axis is the model accuracy. Although it's averaged over all epochs, we can probably play with that a little bit more accurately. But what we see is that there's about a -0.3 or -0.4 correlation between human naming latency and model accuracy, which is suggesting that it's struggling in a way that's more or less consistent with human behavior, or at least similar, correlated. A lot more work needs to be done for these things. So, and then finally, most importantly, our wonderful team of people. Thank you all for helping. So these are students that work in the computational intelligence lab. They've been very helpful. Mohammed is actually a collaborator from the University of Connecticut, but he's also been helpful as well. So that's the talk. If you guys have any questions, I would love to chat about them. Thank you for your attention. Spelling?
Yeah, you mentioned.
The model. What the-
Oh, why is the task spelling? That's just a very interesting area of research for many people. In particular, they want to try and I'll just put it this way. Finding out which reading programs are effective is very expensive and very difficult. You got to pay teachers to go in. It takes multiple months. You got to get IRBs. The data is noisy and messy. People make mistakes. The analysis is complicated. wouldn't it be great if you could just snap your fingers and have an artificial student in your computer where you could run 10,000 simulations and then wipe its memory and then teach it 10,000 more times with 10,000 different programs, right? So if we succeed, this line of work would enable a more like symbiotic relationship between simulating which program reading programs would be effective and then encouraging practitioners to go validate those findings. Like, these 3 programs seem to be the best. You should probably focus your effort on these instead of, because of how expensive it is to do the studies. Yeah, that's one of the motivating principles among the numerous just interesting scientific questions in that space. Good question. Yeah.
You asked a question regarding what kind of tokenizer do we use for this because we are interested in spelling. Is it like the word tokenizer because we want the entire word to be?
So we use the character-based tokenizer because you fundamentally, I mean, in theory, and I assume somewhat clearly, in theory, you must have access to the character level fidelity or resolution to be able to correctly pronounce phonemes. So our model ingests words at the character level. Yeah. Good question. Yeah.
So you were talking throughout the whole talk, a lot of it really seems to shape onto how we think early language development happens, right? Still learning. So is this model, does it start from there, or does it just start, you have some priors that are built in about like vocabulary and sentence structure, whatever, let's say, like how old is the model supposed to be, 5, 6?
It's an excellent question. Yeah. So it starts randomly initialized, which I think in some weird analogy might be the equivalent of an infant with just kind of random neurons where it's all being arranged. So, and we start training from there. One experiment that we're very interested in doing is, what if we pre-train the model on phonology only? So P to P, which is what we do, right? Kids, they hear, they speak, they imitate, and then later they map their internal phonological representations onto orthography. So it'd be very interesting using this multimodal architecture, because we can use either pathway at any point in time, which is one of the other novel contributions of this architecture, is we can do multiple experiments. Pre-train on phonology and then do O to P, or we can do O to P, P to O, O to P, P to O, which is simulating teacher forcing, where the student tries to pronounce, the teacher's like, no, 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 it's cat or something like that. So there's a lot of different types of experiments that can be run. But to your question, yeah, I don't think we have enough information yet to really kind of map it to any sort of developmental process, other than it's randomly initialized. And then we just train it on the words in the order that they show up in most reading texts. And it's a good question.
And I think for the question that, do you add any constraints to the model to, like, for example, we know that morphology is really relevant. Like, do you try to give morphological units more relevant than other things? Like, are there any constraints that you use or not really? I mean, I guess frequency probably, right? Because the words that the model is seeing are not uniform. Like,
yeah, one of the only ones is sort of an implicit frequency weighting by how frequently the words occur in corpus. But that's part of the reading program, which is environmental. So that's kind of separate from the model itself. So okay. I would say in the model itself, though, no, I don't think so. I mean, you guys have helped me work on this and heard me talk about it. Are we doing anything like that? No.
I would say that.
Okay. Yeah, I don't think so. It's just a raw transformer-based model with this architecture. We compress everything into this hidden layer and make sure that this layer is enough to reconstruct both phonology and orthography uniquely. Yeah, no, good question. Anything else? I think we're 2 minutes and we're out of time here. Anything else?
Yeah, I think it'd be really cool to correlate the stages of development with some of the model training steps, and just.
I think that would be a very interesting subsequent experiment. Yeah, we would need a lot of data on child development patterns, and then we can compare some of our results with those. That'd be good. If somebody here has that data, that'd be nice, huh? Yeah.
I have a lot of speech language samples come from the cookies, sciences and so on. But I'm thinking beyond even this, like a future step, where children are deaf, and they cannot process the phonemic.
Oh, interesting.
So maybe bypassing the phonology onto something more meaningful, which is the morpheme chunks that will be associated with, maybe that would be a faster path to enhance their literacy skills through morphology, since their weaknesses in phonology.
Yeah, that's very interesting. I think another, hopefully one of the benefits of having a model like this is we can like lesion certain pathways and put in other options to see which ones the model leverages while trying to solve tasks. That'd be great. Yeah. Well, thank you all for your attention. Please grab some pizza on the way out. And if you have any ideas or data sets or want to collaborate, I'd love to hear from you. Shoot me an email or anything. Yeah, please. That'd be great.